Welcome back, ladies and gentlemen. We're going to be continuing now with intermolecular forces, which looks almost the same as the other unit, which was intramolecular forces. So what in the world is going on? So during our discussion of the states of matter and the kinetic molecular theory, we mentioned that the forces between particles, but we didn't really name them in any way. Right? I said that particles in the kinetic molecular theory, gases, they bounce off each other, but they don't really stick. Well, why would they have stuck at all? Because there's some sort of force between the particles. And we talked about the fact that solids stick together very well. So there's a lot of force between those particles. And we said that liquids stick together like a little bit, but not a lot. So there's a lot of talk about stickiness. There's a lot of talk about things being attached to each other, but what are they? Let's take a look. Chemists group these unnamed forces into two broad categories, the intramolecular forces and the intermolecular forces. Oh, good. Two words that are a lot of letters with only one difference. This one is RA, this one is ER. Thanks, scientists. All right. Intramolecular forces occur within molecules. So inside of a molecule is the intramolecular forces. Intermolecular forces occur between the molecules. We can think of it this way. These are intermolecular forces. These are intramolecular forces. So, for example, in the last lesson, we talked about polar bonds versus non-polar bonds in covalent bonding. All of that is intramolecular forces. Just like, say, well, intra means within. It's in Greek again. Intramurals. So the sports you do inside the school rather than you going outside the school in order to do sports with other teams against other, divisions and stuff. That would be international sports. Oh, international, between nations. So inter is the forces between particles. Intra is the forces within particles. Okay, that's not so bad. So, generally speaking, intermolecular forces, IMFs, are weaker than intramolecular forces. Intramolecular forces are what bind atoms together into chemical compounds. And those are generally pretty hard to break. You need to do chemistry to break those apart. However, intermolecular forces that bind multiple, say, water atoms together, those are a lot weaker. We can break those up by just heating the thing up. And then once we heat it up even just a little bit, water might turn into steam, or ice might turn into water. The intermolecular forces determine if a compound is a gas, a liquid, or a solid at room temperature. These forces are responsible for holding water molecules together to form droplets, or holding cellulose particles together in paper, or graphite together in a pencil. Yeah, most students seem to think that pencils are lead because in the old days pencils were made of lead, and so the name stuck, a lead pencil. They're not. They're actually made of graphite, the same stuff that makes up diamonds, actually. I wonder how that works. If only we had a unit where we talked about solids in great detail. Oh, we're doing it in this unit, just not yet. Patience! So we already discussed with the electronegativity that there's a connection within a compounds are quite strong, and there's a lot of options. There's this rainbow of options, right? So over here we've got our sodium chloride, over here we've got our double oxygens, and over here we've got our like hydrochloric acid kind of thing, right? H and Cl. Intermolecular forces, there are sort of a couple different options, right? So these are the ones that depend on things, okay? So we're going to continue to expand on our rainbow because now we're going to talk about the reactions between molecules, between particles. Previously it was just inside the particle, but here it is what's going on between them. And you see, once again, we've got our rainbow, and once again I've put a dividing line, and here we've got an ionic-ionic interaction. Here we've got something called a hydrogen bond. Here we have a dipole-dipole, and down here we have a London dispersion. Now you'll notice this one's way on the far side, and this one's on this side. So obviously this one here is going to be the most covalent. This one's going to be the most ionic. It's got ionic in the name. But what do they mean? What do they do? Let's talk about them in detail. These two involve polar covalent compounds. Okay, so remember, polar means that there is a positive-ish side and a negative-ish side. So these two here involve positive, negative-ish, partially positive, partially negative sides. Conversely, the one down here is only for nonpolar compounds. And of course, ionic compounds deal with ionic bonding. Okay? So what's happening is, of course, particular compound is made, right? Let's use markers that click. A particular compound is made, right? We take our oxygen and our carbon and we put it together, we make our carbon monoxide, and this is a polar compound. And then if I bring this polar compound close to another polar compound, another carbon monoxide, something will happen between them. It won't be a bond. It's not like they're going to connect together, but they will have some kind of an interaction. And that interaction is going to be based on their partial charges, their polar character. Something kind of like this, as we're about to see. So this is the overview of all the options. Now let's take a look at them in detail. Oh yes, these ones over here are very strong, ionic forces, whereas things like London dispersion are very weak. Okay, so we're going to see that as we go. So let's start with ionic. Right? Ionic forces are honestly almost to the point where it's hard to tell where one molecule ends and another begins, right? Because as we see in this picture, every one of these chlorines is negatively charged, which means every one of these chlorines is going to attract as many sodiums as can fit around it. Same with the sodiums. They're positively charged. So every chlorine that can is going to try to squeeze around them. So, like, where does the one molecule start and end? Do I say, for example, that these two here are one molecule and this is another one? Or do I say that this is one and this is another one? Or do I say that this is one and this is another one? I don't really know. And that's why these forces are so strong. And they're all based on basically the same idea as any kind of electrostatics or any kind of attraction between positive and negative charges. They just sort of clump up around each other and do things. And that's what we see. Ionic molecules, like salt, sodium chloride, are held together by the attraction between opposite charges. An ionic bond forms when a positive cation and a negative anion are attracted to one another. As a result of this, you get stuff like this. But lots of these particles are attracted by the opposite charges. These are called ion-ion bonds and are the strongest type of these intermolecular forces, to the point where they almost don't even count. Almost. Now we've got ourselves some dipole-dipole forces. Okay, well, we got the word dipole in there twice. So in the previous slide, we saw ionic-ionic forces, and that was between two ions. So a dipole-dipole force must be between two dipoles. So if we just knew what a dipole was, we'd be done already. Let's take a look. These occur when polar molecules are attracted to one another. Oh, polar, we know what that is. Polar means that one side is mostly positive and the other side is mostly negative. Okay, so if I've got a compound in which one side is mostly positive and one side is mostly negative, when I bring two of them near each other, they're going to attract in some way. How? The electrical attraction involved occurs between the oppositely charged region of the polar molecules. So the negative of one attracts the positive of another. Not so strongly that they bond together in a chemical bond, but strong enough that they're like, I don't really want to leave. You're a pretty nice person. I kind of want to be your friend. Can we be friends? Especially because on the other side of the molecule, the same thing is happening with those two. So, it's like they're sharing and they're making new friends while at the same time, it's like two couples. So here we've got husband and wife, and we got another husband and wife here because they're both opposites in some way, and they end up being attracted to people from the other molecule, but they're just friends because they're not going to do anything else. This is a clean chemistry. Now, similar, but much weaker than the ionic bonds. Why? Well, because they don't have a full positive and a full negative. So they're only partially attractive. So it's sort of like, wow, that person's really interesting and I like talking to them, less than, wow, that person's really interesting, I'd like to get married to them, which is what we sort of saw in that little cartoon that showed ionic bonding. So as a result of this, these type of forces are stronger than the London dispersion forces that we're going to see later. This is kind of what it looks like, right? The negative chlorine here has got a strong connection to this hydrogen, but it's got a weak connection to this other hydrogen. So this is what we mean when we say a dipole-dipole interaction. It's a connection between two polar molecules. So a dipole, as I just said, is another name for sharing electrons unevenly. So polar molecules have a dipole. There it is. This region over here is electrically poor, so it's overall kind of positive because you can see those protons over there, right? Because all the electrons are being pulled over here to the electron-rich side. The net result is that we use the lowercase Greek letter delta to mark the dipole. See, I knew I had a slide for this. It's just in the wrong section. So we now have another type of bonding called a hydrogen bond. What is a hydrogen bond? Well, think about the name there, right? Hydrogen's in the name. A version of the dipole-dipole that involves hydrogen. Okay, so we know what a dipole-dipole is. That's when we've got two opposite polar molecules and they end up lining up so that way the negative and the positive end up getting near each other and the negative and the positive get near each other. Okay, so that's our dipole-dipole. But now what I'm saying is instead of it being carbon and oxygen, I'm saying it's going to be, say, oxygen and hydrogen. That's the only requirement. One of the two of them has to be hydrogen. Well, much like before, these two, the two hydrogens, are going to be more positive, so it's going to flip, and they're going to align like that. Or, maybe they'll be like long like this. Doesn't really matter. The idea is, though, the opposites attract. This is the strongest type of intermolecular force. It is extremely strong for a dipole-dipole because the positive hydrogen and the negative of whatever else it's attached to are so extreme. Basically, the hydrogen's a bit of a wuss, and the oxygen or the fluorine or the nitrogen or whatever is stealing the electrons so much that the hydrogen is like, I am so cold, I have no coat. All of my shells have been taken away. All my electrons are gone. And yet, I'm not an ion, I get like a corner of the coat for myself. So the net result is that this is a strong dipole, and because it's almost ionic, it ends up behaving in this way. It's not really a bond. I know it has the word bonding in it, but it's not a bond like these are bonds where they're connected together and you have to do chemistry to break them apart. They're just called a bond because they're really strong. The strength of the hydrogen bond depends on the size of the molecule in question. So here's a good old water, and here you can see how we draw a hydrogen bond. We use this hash mark like this. So this oxygen is, of course, sort of like, that's all right, I got two electrons from two other hydrogens, but then it's like, you know what, a third hydrogen could be my friend as well. I like lots of friends. So this partial charge and this partial charge are attracted to each other. The fact this happens for water is incredibly important. Without hydrogen bonding, water would not be a liquid at room temperature. Wait, what? Why? Water is very light. It's 18 grams a mole. Other materials that are twice the mass of water, like carbon dioxide, 44 grams a mole, are a gas because they lack hydrogen bonds holding them together. Remember, carbon dioxide is symmetric by geometry. We talked about that last time. Carbon dioxide looks something like this, right? There's one carbon in the middle and there are two oxygens on either side. So what ends up happening is that the carbon dioxide is perfectly symmetric. So it doesn't have any kind of polar bond in any way. It can't make a dipole. So there isn't a lot of attraction between individual molecules of carbon dioxide. So this carbon dioxide won't be attracted to another one. It'll just float away. It doesn't really care. But that means that it's much harder for the different particles to stick together. And if I don't stick together, I don't make a liquid or a solid. That's how I do it. Water, on the other hand, sticks together incredibly well. Water has these hydrogen bonds, just as we saw on the previous slide there. And these hydrogen bonds connect not just one to another, but every water molecule to every other water molecule in a giant arrangement. This is also kind of why ice floats. Usually a solid is more dense than its liquid, usually. but the hydrogen bonds force the molecules apart in the ice, and that lowers the density. Basically, when they're in a liquid form, the different hydrogens and oxygens can get closer to each other. They're sort of bumping into each other. It's like a crowded bus or something, which, I mean, we don't see a lot of those right now. But it's like a crowded bus. So they're jostling into each other, they're bumping around. But once they start to like spread out and they start to form an ice, then they can start to sort of like space themselves out, feel a little more comfortable, and everything just sort of like settles into place. This is unique. Most materials don't do this, and it's entirely based on these hydrogen bonds, which are just a special form of dipole-dipole interactions. So here is what ice would look like. The different water particles are located close to each other in a very careful organization. Here's water. Some of the particles are in nice organization, others are just randomly oriented, because remember, kinetic molecular theory tells us particles move randomly. These guys are stuck. They can't move. It's like you guys being told you have to sit in your desk and you can't leave. Oh wait, that happens all the time. There's our analogy. You guys are in the hallway getting ready to come into class. When you're in the hallway, you're all jostling up next to each other under normal circumstances, and you're all getting close to the door trying to get in. The moment the door opens, you guys file in and you go and you find your seats. And when you find your seats, the seats are already spaced out. They're nice and comfortable. You get to sit in your desk, get to pull out your stuff. You've got everything around you. You've got room set up for you. The same thing happens between water and ice. The water is jammed together. The ice has a chance to spread out and find itself in a nice organized arrangement. And that organized arrangement only happens because of the hydrogen bonding. All right, there's one more type of force, the London dispersion force, also sometimes called the van der Waal force. They were discovered by a chap called London and another chap called van der Waal. So the force of attraction between induced dipoles, what does that mean? Okay, it's got the word dipole in it, and we know what dipoles are. Dipoles are when we've got unequal sharing, so one side's more positive than the other, right? But what's induced mean? So this exists in all molecules. It's generally very important in diatomic molecules because they are non-polar. This still doesn't explain what induced means. Let's see if we can keep going. Increased force with size. Okay, so the bigger the particle, the more we see this, but we still don't know what it is. If they're strong, you get a very high melting or boiling point. Okay, well, we already know that. If there are strong forces connecting things together, then it takes a lot of energy to split them apart, right? And it's caused by the movement of electrons. Okay, we're finally finding out what induced means. Let's see. Look at the halogens. Fluorine and chlorine are gases. Bromine is a liquid. Iodine is a solid. That seems interesting. That might be connected to that whole high melting point if the forces are stronger and that the forces increase with size. Fluorine and chlorine are at the top of the list. They're pretty small. Iodine is at the bottom of the list. It's pretty big. So the bigger it is, it becomes more force, so it becomes solid. But I still don't know what induced means. So as mass increases, the London dispersion force increases, pulling the molecules closer together and making it harder for the thing to melt or to turn into a gas. Okay, enough of that. What does induced mean? Dispersion forces occur when a cloud of electrons from two molecules come close to each other, and this distorts things. So remember, this is one molecule, this is another molecule. They're both covered in electrons. Now electrons, as we've discussed, they don't like each other. They repel each other. So what happens? As these two come closer together, this guy here pushes, all the electrons on this guy push the electrons away. So the electrons go to the other side of the particle, right? So it's like these two guys are getting closer, and the electrons over here are like, you suck, right? They're insulting these guys. So what do? They go, well, I'm leaving. I don't want to be here. So they go to the other side of the atom. They can't leave, but they go as far away as possible. But this exposes the inner nucleus. And now this inner core, made of positive particles, starts to grab on to these other electrons and is like, hey guys, all the electrons left, I don't know why don't you guys come over and hang out? Now the pull isn't strong enough to pull any electrons off of this guy, but it's enough to pull the electrons that we see here closer. So the net result is that we get the electrons bulging towards this positive, which you can see causes a chain reaction. Now this side is positive, so if another one is coming in, it gets pulled in. This attraction between these opposite charges like this is the same as a dipole-dipole interaction. The difference is in a London dispersion force or a van der Waals force, what we're seeing is that the electrons are creating the dipole. So individually, two oxygen particles coming together are going to be balanced. But if there's another oxygen that comes wandering by, it's going to push the electrons away, and that will reveal positive on this side and negative on that side. That's what induced means. It means to cause or to create. So what we're seeing is that particles aren't static. They don't just sit there. They bond, they fight, they argue, they insult each other to send them away, and then the nuclei attract these guys from over here who just did the insulting towards them. It's quite a messy place, all of these particles. So this is roughly what it would look like step by step. They started off symmetric, then one of them, to be honest, both of them at the same time, triggers an induced dipole, and that triggers a further induced dipole. Now, we said that induced dipoles are stronger if the particle is larger. Why? Well, if the particular molecule is very big, then there's a lot of distance for these electrons to run away. Like right now, these electrons can only run away from like here to there. That's not much room. But if the particle in question was very, very large, right? If we had some kind of an iodine has got a lot of shells, right? It's got tons and tons of shells. So when the other electrons come in, all the electrons that are over here, they can distort and bulge really far over on this side. They've got more room to move because remember, they can't go away from their initial nucleus. They can't leave because this isn't any kind of ionic bonding. But the more space they have, the easier it is for them to get further and further away. Okay, whew, that's a lot of stuff, right? Here's a video you guys can watch, right? It sort of shows a little bit about it. I'll leave it to you guys to load that up. So let's summarize all of this. The stronger the intermolecular forces, remember inter means between, the stronger the forces between molecules, the more difficult it becomes to break the molecules into smaller parts. Therefore, you have a higher melting and boiling point because you need more energy to get those bonds to break. The weaker the forces, the easier it is to break the molecules apart. This means you have a lower melting and boiling point. You require less energy to break all the bonds. So our strongest types of bonds are ionic-ionic bonds. Then we got our hydrogen bonds, then our dipole-dipole bonds, and then finally our London dispersion bonds are the weakest. These intramolecular forces, such as ionic and covalent bonds, are involved. These ones up here are very much like intramolecular, and these ones down here are more like intermolecular. And as a result, this is what we see. We go from a solid to a liquid to a gas, and as a solid, we have a lot of molecular interactions. There's a lot of molecular forces holding that thing together. As a gas, there's almost none. They barely hold together at all. But there's lots of motion and lots of temperature, lots of energy. All right, at this point, you guys can try some intermolecular force practice. I will leave it there, and I will see you guys next time when we are going to talk about phase change. Going from solid to liquid to gas and to plasma. Don't forget plasma's there. Cheers, guys.